Good morning, everyone. Hello, hi. So we're going to present how how chi-square uh how to perform a chi-square or goodness of fit. So the presenters uh Abag, Capa, Torres, and Biado. So what is a chi-square? Uh, What is a chi-square statistic? Chi-square statistic is a test that measures how a model compares to actual observed data. The data used in calculating a chi-square statistics must be a random, raw, mutually exclusive, drawn from independent variable, and drawn uh, from a large enough sample. For example, the result of choosing a pair coin meet this criteria. Chi-square tests are often used to test hypotheses. The chi-square statistic compares the size of any discrepancies between the expected result and actual result given the size of sample and the number of variables in the relationship. For this test, degrees of freedom are used to determine if the certain null hypothesis can be rejected based on the total number of variables and sample within the experiment. As with any statistic, the larger the sample size, the more variable the result. Key takeaways. A chi-square statistic is the measure of difference between the observed and expected frequency of the outcome of a set of events or variables. Chi-square is useful for analyzing such differences in categorical variables, especially those nominal in nature. Chi-square depends on the size of difference between actual and observed variables, the degrees of freedom, and the sample size. Chi-square can be used to test whether two variables are related or independent from another one. It can also used to test the goodness of fit between the unobserved distribution and a theoretical distribution of frequencies. So this is the formula of a chi-square. So as you can see, this is the chi-square equal sum and observed minus expected values square divided by a expected values. So that's it, the formula of a chi-square statistics. Thank you.
Good day everyone, I am Blessy Angela Capa and today I am going to discuss chi-square test, when to use it and how to perform it. So when to use the chi-square test? Well, it depends on the type of chi-square test we are going to perform. The first type is chi-square test of goodness of fit test. It is used if we would like to know if some categorical variable follows hypothesized distribution. It is used when values counts for a categorical variable. For example, suppose we have bags of balls with 5 different colors in each bag. The given condition is the bag should contain an equal number of balls of each color. The idea would like to test here is that the proportions of the 5 colors of balls in each box must be exact. So next is the chi-squared test of independence. It is used if we have one categorical variable and want to test a hypothesis about its distribution. This test examines whether the two sets of variables are likely to be related to each other or not. So, for example, a researcher wants to examine the relationship between gender, male versus female, and empathy, which is high and low. The null hypothesis for this test is that there is no relationship between the gender empathy. And the alternative hypothesis is that there is a relationship between gender and empathy. For example, there are more high empathy females than high empathy males. Chi-square test of goodness of fit is used when the distribution follows a categorical value or variable. And on the other hand, chi-square test of independence is used whether to test two categorical variables are related to each other or not. So it depends on the data or the distribution on how will we use the chi-square test, type of chi-square test. So the next part is how to perform a chi-square test. So how to perform a chi-square test of goodness of fit. The first step is to calculate the expected frequencies. In general, we need to multiply each group's expected proportion by the total number of observations to get the expected frequencies. Step 2 is to calculate the chi-square value from your observed and expected frequencies using the chi-square formula. X squared is equal to summation of O minus E squared over E. So step 3 is to find the critical chi-square value in a chi-square critical value table. Step 4 is to compare the chi-square value to the critical value to determine which is larger. And last step is to decide whether to reject the null hypothesis. If the x squared value is greater than the critical value, then the difference between the observed and expected distributions is statistically significant. On the other hand, if it is less than the critical value, then the distribution is not statistically significant. So the next one is chi-square test of independence. The first step is to use the contingency table to calculate the expected frequencies. Next is to use the Pearson's chi-square formula to calculate for the test statistic. Next step is to find the critical value in a chi-squared critical value table. Fourth is to compare the chi-square value to the critical value. And the last step is to decide whether to reject the null hypothesis or not. So for the first step, to calculate for the expected frequencies, use the formula row R total times column C total over grand total. For the step 2, we can use the formula x squared equals summation O minus E squared over E. In step 3, In finding the critical value, we need to um, remember two terms, the degrees of freedom and significance level. The degrees of freedom is the number of variable 1 groups minus 1 and the number of variable 2 groups minus 1. And the significance level, by convention, is usually 0.05. In step 4, we need to determine if the statistic is big enough to reject the null hypothesis. So we need to compare it to the critical value to find out. So in the last step, if the x squared value is greater than the critical value, then the difference between the observed and expected distributions is statistically significant. The data allows you to reject the null hypothesis that the variables are unrelated and provides support for the alternative hypothesis that the variables are related. And if the x squared value is less than the critical value, then the difference between the observed and expected distribution is not statistically significant. And the data doesn't allow you to reject the null hypothesis that the variables are unrelated and doesn't provide support for the alternative hypothesis that the variables are related. So that ends my presentation of chi-square test on how to use it and how to perform it. Thank you for listening.
Chi-square. Limitations of chi-square. The chi-square test is sensitive to sample size, so relationship may appear to be significant when they aren't, simply because a very large sample is used. In addition, the chi-square test cannot establish whether one variable has a causal relationship with another. It can only establish whether two variables are related. Frequently asked questions about chi-square. So who uses chi-square analysis? Since chi-square applies to categorical variables, it is most used by researchers who are studying survey response data. This type of research can range from demography to consumer and marketing research to political science and economics. Next, what is chi-square test used for? Chi-square is a statistical test used to examine the difference between categorical variables from a random sample in order to judge goodness of fit between expected and observed results. And last question, is chi-square analysis used when the independent variable is nominal or ordinal? A nominal variable is a categorical variable that differs by quality, but whose numerical order could be irrelevant. For instance, asking somebody their favorite color would produce a nominal variable. Asking somebody's age, on the other hand, would produce an ordinal set of data. And chi-square is best applied to nominal set of data because they are categorical variable. And as we know, categorical variable is what chi-square is used to.
Hi, I'm George Adrian C. Viado, and I'm discussing what does chi-square statistics tell you. There are two main kinds of chi-square tests. The test of independence, which asks a question of relationship, such as is there a relationship between the student, gender, and course choice. And the second is the goodness of fit test, which asks is something like how well does the coin in my hand match a theoretically fair coin. Now, I will discussing the test of independence. When considering student gender and course choice, a x-squared test for independence could be used. To do this test, the researcher would collect data on the two chosen variables, gender and courses pick, and then compare the frequencies at which male and female students select among the offered classes using the formula given above in a x-squared statistical table. If there is no relationship between gender and course selection, that is if they are independent, Then the actual frequencies at which male and female student select each offered course should be expected to be approximately equal, or conversely, the proportion of male and female students in any selected course should be approximately equal to the proportion of male and female students in the sample. A x-squared test for independence can tell us how likely it is that random chance can explain any observed differences between the actual frequencies in the data and these theoretical expectations. The second is goodness of fit test. X-squared provides a way to test how well a sample of data matches the known or assumed characteristics of the larger population that the sample is intended to represent. This is known as a goodness of fit. If the sample data do not fit the expected properties of the population that we are interested in, then we would not want to use this sample to draw conclusion about the larger population. Now, I will discussing the example of chi-square statistics. For example, consider an imaginary coin with exactly a 50-50 chance of landing heads or tails in a real coin that you toss 100 times. If this coin is fair, then it will also have an equal probability of landing on either side, and the expected result of tossing the coin 100 times is that heads will come up of 50 times and tails will come up of 50 times. In this case, x-squared can tell us how well the actual result of 100 coin flips compared to the theoretical model that a fair coin will give 50-50 result. The actual toss could come up 50-50 or 60-40 or even 90-10. The farther away the actual results of the 100 tosses is from 50-50, the less good the fit of this set of tosses is the theoretical expectation of 50-50, and the more likely we might conclude that this coin is not actually a fair coin.